All right, now tonight we're going to take a look at the Flashsort algorithm challenge presented by Topcoder. Now, Flashsort is a distribution sort algorithm similar to bucket sort, but instead of creating a space for buckets, what we're doing instead is we're doing sort of an in-place um, sorting method. We have a set of memory that's set aside as an auxiliary vector that allows us to do some shuffling, but overall, this should be linear computational complexity sort. Now, a lot of this method is derived from the Wikipedia algorithm. So you'll notice my notes are N, M, and L, and this is all coming from the Wikipedia uh, write-up of this. Um, and then, uh, so let's go ahead and go through the method. So what I'm going to do is I'm going to test the method first. So bundle exec rspec. Okay, and as we can see, we get 7 examples that are tested and there are 0 failures. So we are getting a sort through here. Now, what Flashsort does is rather than taking each of the items and running through this sorting method one by one and redistributing things that way, what it does is it takes the algorithm and divides it into sectors that are going to be classified by their general location in a sorted array. What we have to do first is we need to set a vector. Now this is just the auxiliary vector that we're going to be using to notate these classifications. Now the auxiliary vector is just a new array that is the size of the factor or the m value that we're passing in, and it's going to be initialized all at 0. Each of the items in the new array will be initialized at 0. Okay, then we are going to go ahead and classify each of those items in the original array. Now we do this by creating this class value, and this class value is going to be set to the factor minus 1 divided by the array max. Now the max is going to be set to 0 currently, minus the min, and the min value is the point at array 0, and we're going to set that to float. Now the reason we're setting it to float is because if it's an integer as it is divided in, then we lose some of the place values, and all of our calculations will be off by those class values. So we need to make sure that we set that value to float when we pass it in. Okay, then over the length of the algorithm, and again the length is just the length of the array, and if you take a look at Wikipedia, that's your value n. And over the length of the array, we are going to set a new value, k, and k is going to be equal to the class, and that's what we just calculated up here, times the array, times the value at array position j, and that's just the array position that we're going from 0 to length, minus the min, and again we're setting this to I. Basically we're finding the floor of this value, so we just set it to integer, so it just goes to the floor value. And then the auxiliary value, k, so remember k, or the auxiliary value, is just this vector that's going to, or this array that will hold what classifications are what when we get to starting to sort this. Then from value 1 to up to the factor. Now that factor is that m value that we'll see on Wikipedia, or that you can see on Wikipedia, and this factor is just the length of the array times 0.43. Now anything between 0.4 and 0.5 will give us a valid value or an accurate value. But reading over several articles, 0.43 was pretty much the optimal value for this factor. So up to the factor. Now this factor is not very high for a very small algorithm or a very small starting array, because it is only less than half the size of the length. So if your array is only 6 values, then factor will be like 2 or 3. So again, or just it will be 2. So 1 to 2 is just one value. So again, this is just something that we're going to be playing around with, and it's just checking the values for the auxiliary vectors that are going to be passed in here. Okay, now after that or just doing a swap with the hold here, we could just do a parallel swap, but here I just went ahead and did a just the normal temporary swap. So you have hold and array hold equals array max, and that's just that temporary value. Then array max will be equal to array 0. So array max is becoming array 0, and array 0 is becoming hold. Now I could just go ahead and just make this a parallel swap, so we can actually see if it still works. So array max array 0 should equal array 0 array max, and should still get the same values here. As you can see, it works. So let's just make that a little bit cleaner code and just keep that as a parallel swap. Okay, so the next that we're going to be dealing with are permutations. Now, permutations just moves the elements in this array to its correct class. So once we have the classes separated out, then we need to move the remainder of the values into its correct class. Now the class is created through a sector of the array. So if we have our factor of 2, then we're only going to have 2 values. If we have a factor of 4, we'll have 4 separate classes, etc. So again, that factor will help us set up the number of classes that we're going to be dealing with. And the permutation is just going to move the items in the starting array to its correct class. It's not quite sorted yet, but it's in a general location. So again, that's just what the permutation is doing, is it's moving those values from its original location in the starting array to its class location. So again, it's the general area of where the number should be in the array when we finish. Once those permutations are done, then we are actually doing the insertion sort. So from we already have the minimum value, so 0 is already in place. We should already have the maximum value, so the maximum value is already in place, but we're going to run a check on that through the length of the array. So we will run from 1 to the length, and we create that temporary hold value, and it's going to be equal to array j. And then what we're going to do is we're going to test the values in each class against its upper and lower limits using this while loop here. And if we need to swap, then we will. And then finally, we can actually see the array as it's being printed out. So this is all the values here that we're actually seeing, but let's go ahead and clear the screen. Once the insertion sort has completed, then we do in fact have our sorted array. Alright, so we've already run the RSpec test, so let's just run it one more time. So we do actually see that it works, so we'll clear our screen, and then we'll open this up just a little bit, and just like I do with my other sorting methods, I create a shuffled array from -100 to +100 of 10 values, and this is just to show you that it works with as many numbers as we want. I could even make it 20 values, and let's go ahead and do that this time. So again, clear the screen, and we will run our flash sort using 20 values from -100 to +100. Okay, so as we can see, these classifications have been set. We have these values from -100 to +100, and it sets the minimum and maximum values, and then it sets the points for the remainder of those permutations. So you can see that these numbers, if you take a look at the numbers, once they're in their classes and permuted to their respective locations, they don't move around a whole lot through that while loop until they need to be inserted into their particular location. So notice that -99 doesn't move the entire time it's been located. Then once -98 has been moved, there's no real movement beyond that. And so we can see as the numbers move their way through the array, we don't have that many iterations that are being printed off. And each of the locations, again, once they're in their classes, they're not a whole lot of movement around. But in the array, they may be swapped and held into the vector, but not a whole lot is being held while they're doing the swap. And then once they're all swapped and inserted in their appropriate locations, we get back this nice sorted array at the end. Okay, so let's go ahead and look at that with a much smaller value. So let's just do 6 from -100 to +100. Do it one more time. And our smallest number is -93. And then our largest number is 49. So as it's going through the array, it's putting each of these things in its location or in its correct class. So 1 looks like it's good, 49 looks like it's good, then it goes -81, oh wait a minute, that it's a little bit smaller. 16 goes by the 1, which we already know is there, and then -93 comes around and we say, oh wait, -93 is less than -81. So again, all of these insertions are made until it finds its correct location. But again, not a whole lot of swaps have happened from the point where everything has been placed in its class to the insertion. And there we have it. Now we do know that insertion sort is big O to the n squared at its worst case scenario, but with smaller arrays, what we see is that insertion sort again works at a much more efficient rate than any other sort, which is a quick sort or anything like that, which is O n log n time complexity. And so what we're having here is, as we get these classifications are rather small arrays, and once everything is placed within that correct classification, or that correct class, sorry, then the smaller arrays are then insertion sorted at a very efficient rate, and we have, once everything's complete, then the insertion sort of those smaller arrays will all be in sorted order, and each of those smaller arrays have minimum and maximum values within that class, and leading into the next class, which will always be less than or greater than, sorry, the previous class. So once everything has been insertion sorted, then everything should be in sorted order, but again at a much more efficient rate than trying to insertion sort the entire array. So there you have it, flash sort in a nutshell. Again, if there are any questions or comments, please feel free to post them in the forum, and I'll answer them as soon as possible. Thanks, guys.